We like to think we know our place in the universe. We've mapped the stars, calculated the age of everything, and built models that explain galaxies and black holes with staggering precision. But every now and then, the universe reminds us just how little we actually understand. And one of those reminders is a quiet, unsettling realization: we might be living in a bubble. Not a metaphorical bubble of ignorance, but an actual physical void in the fabric of space itself. A region so vast and so empty that it challenges some of the most fundamental assumptions in cosmology. This is the story of the KBC void, a cosmic desert 2 billion light-years across, and why its existence could rewrite everything we thought we knew about the universe, about the expansion of space, and even about the search for extraterrestrial life. Let's start with the scale of things. You've probably heard the numbers before. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars. That's a number so large it's almost meaningless. To try to grasp it, imagine if every one of those stars had at least one planet. That would mean hundreds of billions of worlds just in our own galactic neighborhood. Now multiply that by the estimated 2 trillion galaxies in the observable universe. The total number of planets out there is almost incomprehensible. Some estimates suggest there are more stars in the universe than grains of sand on every beach on Earth. And if even a tiny fraction of those planets are in the habitable zone of their stars, the number of worlds that could support life becomes enormous. So, where is everybody? This is the Fermi paradox in a nutshell. The universe should be teeming with life, or at least with technological civilizations sending signals across the cosmos. But we have heard nothing. No definitive alien broadcasts, no laser pulses, no Dyson spheres. The sky is silent. For decades, scientists have proposed countless explanations. Intelligent life destroys itself. Civilizations are too far apart. Or maybe we are alone after all. But there is another possibility, one that has gained traction only in the last decade. What if the reason we haven't found anyone is not because they don't exist, but because we happen to live in the cosmic equivalent of a remote village far off the galactic highway? What if we are inside a void so large and so sparsely populated that other civilizations are simply too far away to notice us, and we are too far from them to hear anything at all? That idea might sound like science fiction, but it is grounded in real astronomical observations. In 2013, a team of researchers, led by Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper with a startling conclusion. By analyzing the distribution of galaxies in the nearby universe, they found evidence that our Milky Way is located near the center of an enormous underdense region, a void. And not just any void. This one, now known as the KBC void, named after Keenan, Barger, and Cowie, is about 7 times larger than typical cosmic voids. It stretches approximately 2 billion light-years from end to end. That is so big that if you were to travel at the speed of light from one side to the other, it would take 2 billion years. To put it in perspective, the entire observable universe is about 93 billion light-years across. This void occupies a significant fraction of our local cosmic neighborhood. Before we dive deeper, let's clarify exactly what we mean by a void. In astronomy, voids are regions of space where the density of matter is much lower than average. The universe, on large scales, is not a uniform soup of galaxies. Instead, it has a structure that looks something like a cosmic foam. There are dense clusters of galaxies connected by filaments, and in between those filaments are vast, empty spaces called voids. A typical void might be a few 100 million light-years across and contain only a handful of galaxies, or sometimes none at all. The KBC void, however, is not typical. It is a supervoid, a region where the galaxy count is about 20% lower than the cosmic average. That might not sound dramatic, but it is statistically significant. Within this void, there are far fewer galaxies and therefore far fewer stars than in the regions outside. And because we are near its center, our view of the cosmos is filtered through this local emptiness. Now, you might have heard conflicting information about the Milky Way's location. Some sources say we are in a void. Others say we are in a local group of galaxies that is part of a larger supercluster. So, which is it? Let's untangle this. The Milky Way is part of the local group, which includes Andromeda and about 80 other small galaxies. The local group is, in turn, part of the Virgo supercluster, a much larger structure containing thousands of galaxies. But even the Virgo supercluster is embedded within an even larger structure called the Laniakea supercluster. So we are certainly not in an empty void in the sense that there are no galaxies around us. In fact, our local environment is quite dense compared to the deep voids far away. However, when scientists look at the distribution of galaxies on scales of hundreds of millions to billions of light-years, they find that our region is underdense compared to the average density of the universe as a whole. It's like living in a small town in the middle of a vast desert. The town itself is not empty, but the region around it is far less populated than the fertile plains elsewhere. So, the KBC void does not mean we are alone in our immediate neighborhood. It means that on very large scales, we are situated in a region that is sparser than the cosmic norm. This discovery was met with considerable skepticism at first. The standard model of cosmology, known as LCDM, Lambda Cold Dark Matter, is built on a cornerstone called the cosmological principle. This principle states that the universe is homogeneous and isotropic on large scales, meaning that matter is distributed evenly and looks the same in every direction. The existence of a void as large and as deep as the KBC void seems to violate that principle. If the universe is truly homogeneous, how can there be a region 2 billion light-years across with a significantly lower density? Cosmological simulations based on LCDM, such as the Millennium simulation or the MXXL simulation, suggest that structures like the KBC void should be extremely rare. In fact, the probability of such a void forming within the standard model is less than 1%. That immediately raises red flags. Either our observations are wrong, or our model is missing something. But as more data poured in from galaxy redshift surveys that measure the distances and motions of thousands of galaxies, the evidence for the void became harder to dismiss. The KBC void is not just a statistical fluke. It is supported by multiple independent studies. In 2017, a team including Ryan Keenan published an updated analysis confirming the underdensity out to a distance of about 300 megaparsecs, or roughly 1 billion light-years. They found that the matter density in that volume is about 20% lower than the cosmic average. And crucially, this underdensity is not uniform in all directions. It has a structure that influences the apparent motion of galaxies, a phenomenon known as the bulk flow. Galaxies inside the void are being pulled toward the denser regions outside, creating a velocity field that we can measure. This brings us to one of the most exciting implications of the KBC void. It may offer a solution to the Hubble tension. The Hubble tension is arguably the biggest crisis in modern cosmology. To understand it, we need to talk about the expansion of the universe. The universe has been expanding since the Big Bang, and the rate of that expansion is given by a number called the Hubble constant. Think of it as a cosmic speed limit. For every megaparsec, about 3.26 million light-years, farther away a galaxy is, it moves away from us faster by about 70 kilometers per second. But here's the problem. There are two different ways to measure HO, and they give different answers. The first method uses observations of the early universe. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists can infer the conditions of the universe about 380,000 years after its birth. Using the standard LCDM model, they can then extrapolate forward to predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. The second method uses direct observations of nearby galaxies. Astronomers measure distances using standard candles like Cepheid variable stars and Type Ia supernovae, and then measure how fast those galaxies are receding from us. This method gives a value of about 73.0 kilometers per second per megaparsec. The difference is about 8%, and it is statistically significant. It cannot be explained by measurement errors alone. This discrepancy is the Hubble tension. It suggests that either our model of the early universe is wrong, or our understanding of the local universe is incomplete. And that's where the KBC void comes in. If we are living inside a large underdense region, then the expansion rate we measure locally might not be the true cosmic expansion rate. Here's why. Inside a void, there is less matter, so the gravitational pull is weaker. But the surrounding denser regions exert a stronger gravitational attraction, pulling matter outward. This creates an extra apparent motion, making it look like galaxies are moving away from us faster than they actually are. In other words, the void fools us into thinking the expansion is faster in our neighborhood. When scientists model the gravitational effect of the KBC void, they find that the local expansion rate measured from nearby galaxies could be inflated by about 10% compared to the true global expansion rate. That is almost exactly the size of the Hubble tension. So the Hubble tension might not be a sign of new physics like modified gravity or exotic dark energy. It could be a simple geographic effect. We happen to live in a place that skews our measurements. This is a Occam's razor solution that many cosmologists find appealing because it doesn't require us to throw out the entire LCDM model. However, this explanation is not without its own problems. For the void to have such a strong effect, it must be quite deep and quite large. And as we already mentioned, standard LCDM simulations struggle to produce voids of this size and depth. So, the void explanation for the Hubble tension actually compounds the original problem. We now have to explain why such a void exists in the first place. This has led some researchers to consider alternative theories of gravity. One of the most prominent is modified Newtonian dynamics, or MOND. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter. It suggests that at very low accelerations, like those found at the edges of galaxies, gravity behaves differently than Newton predicted. When applied to cosmological scales, MON predicts that structure formation happens faster than in LCDM. In a MOND universe, large voids like the KBC void are much more likely to form because gravity is stronger in low-density regions, causing matter to clump together more efficiently. So, the existence of the KBC void could be seen as evidence in favor of MOND. But MOND also has its own difficulties. It cannot fully explain the cosmic microwave background or the large-scale clustering of galaxies as seen in surveys like the Sloan Digital Sky Survey. The debate between LCDM and MOND continues, and the KBC void sits right in the middle of it. Now, let's turn to the Fermi paradox. How does living in a void affect our chances of encountering extraterrestrial intelligence? The classic argument is that if the universe is teeming with civilizations, we should see some evidence of them, whether it's radio signals, probes, or megastructures. But if our galaxy is situated in a vast underdense region, then we are effectively isolated. The number of galaxies within the KBC void is lower than average, which means fewer stars and fewer potential habitable planets. Even if intelligent life is common in the universe, it might be concentrated in denser regions like the Virgo supercluster or the Great Attractor region. Our local group of galaxies might be a backwater. The distances to the nearest galaxies outside the void are enormous, on the order of hundreds of millions of light years. Any signals from those civilizations would take hundreds of millions of years to reach us, and we have only been listening for a few decades. Moreover, there is an even more speculative idea. Civilizations in denser regions might avoid expanding into voids because they are resource poor, or they might simply be unaware of our existence. The anthropic principle also plays a role here. Some have argued that we should not be surprised to find ourselves in a void, because voids provide a relatively safe environment for life to evolve. In denser regions, galaxies collide more often, supernovae are more frequent, and radiation levels are higher. A void offers a more stable, quiet corner of the universe, where life can emerge without being constantly disrupted by cosmic violence. So, our location in the KBC void might actually be a necessary condition for our existence. This is a version of the anthropic selection idea. We observe a low-density region because only in such a region could observers like us arise. But we need to be careful. The anthropic principle is often criticized as a philosophical cop-out because it can explain almost anything by saying, if things were different, we wouldn't be here to observe them. Nevertheless, when combined with the empirical evidence for the KBC void, it offers a coherent narrative. We are in a bubble of relative emptiness, which explains both the Hubble tension and the silence of the cosmos. This does not mean the void is definitely the answer. Scientists are still gathering data. New surveys like the Dark Energy Spectroscopic Instrument, DESI, and the Euclid mission are mapping the distribution of galaxies with unprecedented precision. In the next few years, we will get a clearer picture of whether the KBC void is a true anomaly or just an artifact of biased samples. One important caveat: not all astronomers agree that the Milky Way is inside the KBC void. Some argue that the observed underdensity is a result of selection effects. Maybe we are just not seeing all the galaxies in that direction because of dust or other observational biases. Others point out that the evidence for the void relies heavily on the Tully-Fisher relation, which is not perfectly calibrated. There is also a rival idea called the dark flow hypothesis, which suggests that the bulk motion of galaxies is caused by the gravitational pull of structures beyond the observable universe, not by a local void. So, the debate is far from settled. The KBC void is a hypothesis, not a proven fact, but it is a hypothesis with strong observational support and profound implications. Let's step back for a moment and think about what it means to live in a cosmic void. The universe is unimaginably vast, and we are just a tiny speck on a planet orbiting an ordinary star in an ordinary galaxy. But if the KBC void is real, then our galaxy is even more ordinary than we thought. It is situated in a region that is emptier than average. That emptiness might be the reason we feel so alone. It might also be the reason we measure the universe to be expanding faster than it actually is. It might even be the reason our theories of gravity and dark matter seem to work so well locally but break down at larger scales. Ultimately, the KBC void is a reminder that our perspective is limited. We are embedded in the universe, not outside it, and our observations are inevitably biased by our location. As we refine our maps of the cosmos, we may discover that we are not at the center of anything special, except perhaps the center of a vast, quiet desert. And that might be the most profound discovery of all. The silence of the universe is not a sign that we are alone, but a sign that we are in a very quiet neighborhood. So the next time you look up at the night sky, think about the void. Those stars you see are mostly in our own galaxy, but beyond them, in every direction, lies an expanse so empty that it stretches for billions of light years. We are surrounded by emptiness, and that emptiness shapes everything we see, every measurement we make, and every search for other minds. It may be the most important thing about our cosmic address. We don't yet know if the KBC void will stand the test of time, it's a confirmed feature of the universe. But the story of its discovery, the controversy it sparked, and the solutions it offers show that science is alive and messy. The Hubble tension remains unresolved. The Fermi paradox continues to haunt us, and the debate between LCDM and Mundi rages on. But one thing is clear: the universe is not as simple as we once thought, and that is exactly what makes it so fascinating. Now, if you've enjoyed this journey through the cosmic void, consider subscribing. Because the universe is full of mysteries, and we've only scratched the surface. From dark energy to the great attractor, from cosmic voids to multiverse theories, there's always more to explore. So stay curious and keep looking up. Because even if we are living in a bubble, it's a bubble that contains everything we know and love. And that's pretty amazing. Thanks for watching. And if you want to dive deeper into the science of voids and the Hubble tension, check out the links in the description for further reading. I'll see you in the next video. Before we wrap up, let's revisit what the KBC void actually means for our everyday understanding of the cosmos. We often think of the universe as a vast, evenly sprinkled collection of galaxies, like raisins in a perfectly mixed dough. But the KBC void suggests that the dough has giant bubbles, and we happen to be inside one. That's a humbling thought. It means our local patch of the universe is not representative of the whole, and that has consequences not just for cosmology, but for how we interpret every astronomical observation we make. Take, for example, the measurement of dark energy. The standard model of cosmology includes a mysterious force called dark energy that is supposedly causing the expansion of the universe to accelerate. That conclusion comes from observations of distant Type Ia supernovae in the 1990s, which won a Nobel Prize. But if we are inside a void, the apparent acceleration might be partly an illusion. The void could mimic the effects of dark energy on the expansion history. Some researchers have even proposed that we don't need dark energy at all if the void is deep enough and we are located close to its center. This is a radical idea, but it has been explored in papers using the timescape model, which argues that the universe expands at different rates in voids and in dense regions, and that our perception of acceleration is a result of averaging over these inhomogeneities. While the timescape model is not widely accepted, it shows that the void hypothesis forces us to question some of our most cherished assumptions. The KBC void also has implications for the cosmic microwave background. The CMB is a snapshot of the universe at 380,000 years old, and it is remarkably uniform. But if we are inside a large void, that void would leave an imprint on the CMB via the integrated Sachs-Wolf effect. As photons travel through the void, they gain energy when entering and lose energy when exiting. But due to the gravitational potential changing over time because of the expansion, there is a net shift. For a void as large as KBC, this effect should be detectable. And indeed, there are hints of a cold spot in the CMB in the direction of the Eridanus supervoid, which is a smaller void. The KBC void might contribute to a larger scale anomaly. So far, the data is inconclusive, but future CMB surveys like the Simons Observatory could help pin this down. Now, let's address the elephant in the room, the conflicting information about the Milky Way's location. You might have heard that we are on the outskirts of the Virgo supercluster, or that we are near the center of the Laniakea supercluster. These are different scales. The KBC void is a much larger structure, billions of light-years across, while the Laniakea supercluster is about 500 million light-years across. So, it's perfectly possible for the Milky Way to be both in a supercluster, a dense region on intermediate scales, and in a giant void, an underdense region on larger scales. Think of it like a foam. There are dense filaments and walls, but on the largest scales, even those filaments are part of a bigger bubble. Our galaxy sits in a relatively dense local filament, but that filament is embedded in a vast, underdense region. That is precisely what the KBC void describes, a lower-than-average density on scales of hundreds of megaparsecs, even though our immediate neighborhood is normal. One of the most cited studies on the KBC void is the 2017 paper by Keenan, Barger, and Cowie. They used a sample of galaxies from the 2-micron all-sky survey, 2MASS, and the 2MASS redshift survey, 2MRS. They found that the number density of galaxies within 300 mpz is about 20% lower than the mean. They also noted that this underdensity is not isotropic. It is more pronounced in certain directions, which is consistent with a void that is slightly elongated. Subsequent work by other teams, using data from the Sloan Digital Sky Survey and the 60th Galaxy Survey, has generally supported this finding, although some studies have found a smaller underdensity of around 10 to 15%. The debate is ongoing, but the key point is that the existence of a significant underdensity in the local universe is now widely accepted. The question is its exact size and depth, And that brings us to the scientific standing of the KBC void. It is not yet a settled fact. Some cosmologists argue that the observed underdensity could be a selection effect. Maybe we are missing galaxies because of dust extinction, or because low-luminosity galaxies are harder to detect. Others point to the fact that the peculiar velocity of the local group, our galaxy and its neighbors, relative to the CMB is about 600 kilometers, which is unusually large. If we are in a void, we would expect a large bulk flow toward the denser regions, and indeed, the observed peculiar velocity is consistent with that picture. But alternative explanations exist, such as the pull from a massive structure like the Shapley supercluster, or even the Great Attractor. The KBC void is just one piece of a complex puzzle. Perhaps the most exciting aspect of the KBC void is how it connects different mysteries. The Hubble tension, the Fermi paradox, the large-scale bulk flows, the abundance of voids in simulations, all these threads come together if we accept that we live in an unusually empty region. This kind of cross-disciplinary synthesis is rare in science, and it makes the void hypothesis very attractive. But it also means that if the void is disproven, we will lose a unifying explanation and be left with multiple separate puzzles. So, what does the future hold? Over the next decade, surveys like DESI will map the positions of tens of millions of galaxies, giving us a three-dimensional map of the local universe with unprecedented detail. If the KBC void is real, we should see a clear signature, a spherical or ellipsoidal region where the galaxy density is low, surrounded by a denser shell. We should also see a coherent flow of galaxies away from the void center. These predictions can be tested. On the theoretical side, cosmologists are running new simulations with alternative gravity models to see if they can reproduce such a void without violating the CMB constraints. If MOND or other modified gravity theories can do it, then the existence of the KBC void becomes a strong argument for revising our standard model. But let's not get ahead of ourselves. The universe has a way of surprising us. Perhaps the KBC void will turn out to be a statistical fluctuation after all, a rare but not impossible event in LCDM. Or perhaps it will be confirmed, and we will have to accept that we live in a very special place, not special in the sense of being privileged, but special in the sense of being peculiar. That peculiarity could explain why we feel so isolated and why our measurements of the expansion rate are off. I want to leave you with a final thought. The idea that we are inside a cosmic void is not just a scientific curiosity. It's a profound shift in perspective. For centuries, humans believed they were at the center of the universe. Then Copernicus moved us to a planet orbiting the Sun. Then we learned the Sun is just one star among billions in the Milky Way. Then we discovered the Milky Way is just one galaxy among billions. Now, we are learning that even our galaxy's position is not average. It's in a desolate region, a cosmic backwater. That's a humbling progression. But it also gives us a unique vantage point. From inside the void, we can see the rest of the universe without the clutter of too many galaxies in our way. It's like being in a dark room with a clear view of the light outside. So the next time you feel small and insignificant, remember, you are not just a speck on a pale blue dot. You are a speck inside a bubble of emptiness that stretches for billions of light years, and from that bubble, you are trying to understand the whole cosmos. That's a remarkable thing. Keep asking questions, keep looking up, and maybe, just maybe, The void holds the answers we've been searching for all along. Thank you for watching. If you enjoyed this deep dive into the KBC void and its implications, please like and subscribe. It really helps the channel. And let me know in the comments. Do you think we are alone because we are in a void? Or is there another explanation for the great silence? I'll read your thoughts and discuss them in a future video. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. But let's push a little further into what this void means for our understanding of life itself. You see, if we are indeed inside a cosmic void, a region with fewer galaxies, fewer stars, fewer planets, then the sheer scarcity of habitable worlds within our immediate vicinity becomes a kind of selection filter. It's not just that we are far from other civilizations because the void is empty. It's that the very conditions that allowed intelligent life to emerge here might be tied to the void's existence. Some researchers have proposed that voids, being less dense, experience weaker tidal forces and fewer violent events like galaxy mergers or supernova blasts. That relative calm could provide a stable environment for planetary systems to evolve over billions of years without repeated cosmic catastrophes. In other words, the void might be a cradle for life, not a desert. Think about that. We may be living in a quiet, protected bubble, an oasis of stability in a universe that is otherwise chaotic and crowded with destructive events. That flips the Fermi paradox on its head. Maybe it's not that we are isolated. Maybe we are privileged. The void gave us the time and space to develop, while civilizations in denser regions might get wiped out by gamma-ray bursts or gravitational disturbances before they ever reach the stage of spacefaring technology. If that's true, then the silence of the cosmos is not a sign of loneliness, but a sign of our good fortune. We are the lucky ones sitting in a cosmic sanctuary. Now, there is a darker twist to this idea. If the void is indeed protective, then stepping outside the void might be dangerous. As we send probes and signals farther into the universe, we are essentially shouting into a dense forest full of predators. The void's very emptiness might be why we haven't heard from anyone else. They might have learned to stay quiet in order to survive. That's a sobering thought, and it adds a whole new dimension to the search for extraterrestrial intelligence. Maybe the reason we haven't found anyone is that everyone who could broadcast has already been silenced by the very forces that our void shields us from. It's a hypothesis that pushes us to reconsider our own future. Should we be broadcasting our presence at all? Are we inviting trouble by sending messages into the denser regions beyond our local hole? These are questions that science fiction has explored for decades, but now cosmology gives them a concrete foundation. Our location inside the KBC void might be both a blessing and a curse. It allows us to exist, but it also blinds us to the dangers lurking just beyond our horizon. Let's also consider how the void affects our understanding of the universe's large-scale structure. The cosmic web, the network of filaments and voids that makes up the universe on its grandest scales, is a direct consequence of the initial density fluctuations after the Big Bang. In the Standard Model, small ripples grew over time under gravity to form the clumpy distribution we see today. The voids are the underdense regions that have been drained of matter by the gravitational pull of the filaments. But the KBC void is so large, about 2 billion light-years across, that it challenges the typical size distribution predicted by simulations. It's like finding a room in your house that is 10 times bigger than any other room, with almost no furniture inside. That anomaly suggests that the initial conditions in our local patch of the universe might have been different. Perhaps we are sitting in a region that experienced a rare extreme fluctuation, one that is statistically improbable but not impossible. And that improbability has deep implications for the Copernican principle, which states that our position in the universe is not special. If the KBC void is real and we are near its center, then our position is actually quite special. It would mean that the universe has a privileged observer, us, in a place that is far from average. That would be a revolution in cosmology comparable to the shift from a geocentric to a heliocentric model. We would no longer be just a typical observer. We would be an atypical observer, and that would force us to reconsider every statistical inference we make about the universe from our local sample. And here is another layer. If we are in such a large void, then the expansion rate we measure locally is not the true global expansion rate. As we discussed, the Hubble tension might be resolved by the void's gravitational effects, but that resolution comes at a cost. It means our measurements of dark energy, which rely on the assumption of homogeneity, could be fundamentally flawed. The entire edifice of modern cosmology, the Lambda-CDM model with its dark energy and dark matter, imagine standing on the surface of a world so isolated that the night sky above you holds nothing but a faint milky smudge of stars, your own galaxy, and beyond that, an endless, absolute blackness. No pinpricks of distant suns, no blur of neighboring galaxies, just the slow, silent drift of darkness in every direction. You would not know, for the first few decades of your civilization's existence, that anything else exists at all. Your telescopes would reveal only the stars of your own home, and then, eventually, a few dim, unresolved clouds that might be entire galaxies, but so far away, so impossibly remote, that they appear as nothing more than ghostly whispers on the edge of detection. This is not a scene from a science fiction novel. This is what reality would feel like if humanity had evolved inside one of the universe's great cosmic voids. We live in a universe that is, by and large, staggeringly empty. If you stand atop the Shard in London on a clear day, you can look south and see the coast of France. The air between seems empty, transparent, but it contains roughly 10 trillion atoms per cubic meter. That is an enormous number, yet we call it empty. Go up 100 kilometers, and the density drops to 1,000,000 trillion atoms per cubic meter. A third of the way to the moon, you find about 7 million atoms. Leave the solar system entirely, and interstellar space, the space between stars, contains approximately 1,000 atoms per cubic meter. Travel even farther, into the space between galaxies, and you are down to just 10 atoms per cubic meter. That is emptier than the best vacuum ever created on Earth by a factor of trillions, and yet that is not truly empty. The space between galaxies is still part of something larger, the cosmic web, a vast network of filaments and walls where galaxies gather in clusters and superclusters. But what about the spaces in between those filaments, the gaps between the largest structures of the universe? Those regions are emptier still, and they have a name: voids. A void is a vast, roughly spherical region of space with a dramatically lower density of galaxies compared to its surroundings. The The technical definition used by astronomers refers to an area where the number of galaxies is about 1/10 the typical number found in the galactic walls and filaments that define the cosmic web. Voids are not structures themselves. They are the empty spaces between structures, but they are a fundamental part of the universe's architecture. The smallest voids are about 10 megaparsecs across. 1 megaparsec is roughly 3.26 million light-years, so a typical small void is about 30 million light-years in diameter. Larger typical voids can reach 10 times that size, 300 million light-years across, and at that scale, we call them supervoids. But even that is modest. Some voids, especially those that form in the low-density regions of the universe, far from the densest walls, can stretch over 1 billion light-years in diameter. To appreciate that scale, 1 billion light-years is so vast that light, traveling at 300,000 kilometers per second, takes 1 billion years to cross it. That is 1/10 the age of the universe itself. The study of cosmic voids began in earnest in the 1970s, when redshift surveys first allowed astronomers to map the three-dimensional distribution of galaxies. Before then, we saw the universe as a more or less uniform scatter of galaxies. But as we measured their distances by the redshift of their light, a structure emerged. Galaxies were not randomly distributed. They clustered into filaments, walls, and nodes, with enormous empty regions in between. The first void to be recognized was identified in the direction of the Coma cluster in the late 1970s. By 1981, a particularly striking example was discovered: the Bootes void, lying near the constellation of Bootes on the edge of the Hercules supercluster. This void was enormous. Estimates ranged from 250 to 330 million light-years in diameter, with a volume of over 200,000 cubic megaparsecs. At the time, its size was so unexpected that some scientists questioned whether there had been enough time in the universe's history for such a void to form. But further observations revealed that the Bootes void is not a single empty bubble. It is the result of two smaller voids merging, like soap bubbles coalescing into one larger cavity. The galaxies that should have filled that space were swept to the edges, leaving behind a nearly empty interior. And yet, it is not completely empty. Astronomers have found about 60 isolated galaxies inside the Bootes void, where thousands would be expected in a comparable volume of normal space. Those 60 galaxies form a tube-like structure running through the void's center, the remnants of the boundary between the original merging voids. To put that emptiness into perspective, imagine driving from the Atlantic coast of the United States to the Pacific coast and passing only a couple of small towns along the way. And that analogy fails because the void is three-dimensional. The Bootes void is so sparse that it has earned the nickname the Great Nothing. If humanity had evolved on a planet inside one of those 60 isolated galaxies, we would not have known that other galaxies existed until the 1960s. That is not hyperbole. Astronomer Greg Aldering of the University of Minnesota calculated that the nearest external galaxy would have been so far away that it would have taken decades of technological advancement just to detect it. Imagine the scientific revolution delayed by half a century because the universe simply appeared empty. Now, let us consider the nature of these voids. How do they form? The answer lies in the first tiny fraction of a second after the Big Bang. During that initial moment, the universe was an infinitesimally small, ultra-dense soup of energy. Quantum fluctuations, random variations in energy density, created ripples across this primordial plasma. Then, an event called cosmic inflation blew the universe up from microscopic to astronomical in a fraction of a second. Those quantum ripples were stretched across vast distances. The denser spots became the seeds of future galaxies and clusters. The emptier spots became the seeds of voids. As the universe expanded and cooled, dark matter began to clump together under gravity, forming a network of filaments. Normal matter followed, condensing into gas clouds, then stars, then galaxies. Over billions of years, the galaxies migrated along these filaments, gathering into clusters and superclusters. Meanwhile, the regions that had been slightly less dense from the beginning were drained of matter. Gravity pulled everything out of those regions, leaving behind vast, nearly empty spaces. These are the voids we see today. Voids are not just empty, they are dynamic. They grow as the universe expands, because the dark energy that accelerates cosmic expansion acts everywhere, including inside the voids. The empty space inside a void expands faster than the denser regions because there is less matter to slow it down. This means that voids become larger and emptier over time. Their size and shape can tell us about the abundance of dark energy. In fact, by studying the distribution of the largest voids in the universe and comparing them to simulations, astronomers have confirmed that about 70% of the universe's energy density must be dark energy, a result that matches measurements of the cosmic microwave background. Voids are, in a sense, the perfect laboratories for studying dark energy because they are simple. No complicated galaxy dynamics, just pure expansion. But not all voids are created equal. Some exist within the dense walls of the cosmic web, carved out by the gravitational pull of merging galaxy clusters. Others are the primordial voids from inflation, sitting in the low-density backwaters. The largest known void by volume is the one we happen to live in, the KBC void, named after its discoverers, Keenan, Barger, and Cowie. This void is roughly 2 billion light-years in diameter, and it contains the Milky Way, the Local Group, and even a large part of the Laniakea supercluster of galaxies. Wait, does that mean we live inside a void? Yes. The KBC void is defined by a lower-than-average density of galaxies compared to the surrounding universe. Our home is in a relatively sparse region, about 20% less dense than the cosmic average. That might not sound like much, but on the scale of billions of light-years, it is significant. We are not in the center of the void, but we are closer to the center than to the edge. This position has direct implications for our observations. Because the surrounding galactic walls are denser, they exert a gravitational pull on us, drawing us through the void toward the filaments. This motion, known as the bulk flow, interferes with our measurements of the Hubble constant, the rate at which the universe is expanding. In fact, it may explain why the Hubble constant measured from nearby galaxies differs from the value derived from the cosmic microwave background. The KBC void is like living in a rural town far from the bustling cities of the cosmic web. The night sky is a little darker, the galaxies a little sparser, but we are still part of the grand structure. Now, imagine if we were not in a mild void like the KBC, but instead inside something like the Bootes void. What would that mean for us? First, the night sky would be devastatingly empty. Our own galaxy would still shine, but beyond it, there would be no Andromeda, no Triangulum, no nearby dwarf galaxies. The nearest galaxy might be hundreds of millions of light-years away. When you look up, you would see only the stars of the Milky Way. And then, after decades of searching with powerful telescopes, you might detect a few faint smudges, those 60 isolated galaxies scattered through the void. But they would be so far that they would appear as tiny, unresolved blobs, not the magnificent spirals we see from Earth. Your astronomers would have to work much harder to discover that the universe extends beyond your own island of stars. Your telescopes would not reveal the cosmic web until much later in your technological history. And because those distant galaxies are moving away from you due to cosmic expansion, the light from them would be severely redshifted, making them even harder to detect. In fact, if you were inside a truly deep void, the expansion of the universe might cause the galaxies on the void's boundaries to recede so fast that they would appear to be moving away faster than the speed of light in terms of recession velocity, and eventually they would vanish beyond your cosmic horizon. Generations of astronomers would live and die before any definitive proof of other galaxies emerged. There is another profound consequence of living inside a void. The cosmic microwave background would look different. The CMB is the afterglow of the Big Bang, a uniform bath of microwave radiation that fills the entire universe. Its temperature varies by a few microkelvins across the sky, revealing the seeds of structure. But if you were inside a large void, the CMB would appear slightly colder in that direction because the photons from the early universe would lose energy as they climbed out of the gravitational well of the void. Or rather, they would gain energy as they fell into the void from the denser surrounding regions. Actually, the integrated Sachs-Wolf effect describes how photons passing through a void or a supervoid get slightly blue-shifted or red-shifted depending on the evolution of the void. In a universe with dark energy, a void that is still growing imprints a cold spot on the CMB. This brings us to one of the most intriguing mysteries of modern cosmology, the CMB cold spot. In the early 2000s, the Wilkinson Microwave Anisotropy Probe, WMAP, mapped the cosmic microwave background with unprecedented precision. It revealed a large, unusually cold region in the sky, near the constellation Eridanus. The temperature difference between this spot and the surrounding warmer ring is about 70 microkelvins, much larger than the average fluctuation of about 20 microkelvins. In some places, variations can reach 140 microkelvins, but the cold spot stood out because of its sheer size and the sharp contrast with its surroundings. Initial speculation ran wild. Some fringe theories suggested it was a bruise from a collision with another universe, or a region where the laws of physics were different. But the scientific community demanded evidence. In 2013, the Planck satellite, with even greater sensitivity and resolution, confirmed the cold spot's existence, ruling out the possibility of a WMAP instrumental error. The cold spot is real. So, what causes it? One of the most compelling explanations is that the cold spot is the imprint of an enormous supervoid, a region of space so large and so empty that its gravitational influence stretches the light of the CMB, stealing a tiny amount of energy from the photons as they pass through. This is called the integrated Sachs-Wolf effect, or ISW effect. In a universe dominated by dark energy, large voids grow over time, and photons climbing out of these voids lose energy, appearing colder. To produce the observed cold spot, the hypothetical supervoid would need to be at least 500 million light-years in diameter, and possibly as large as 1 billion light-years, dwarfing even the Booty's void. It would be the largest void ever found, and it would lie about 6 to 10 billion light-years away in the direction of the cold spot. Subsequent studies have looked for direct evidence of such a supervoid by surveying galaxy counts in that region. Some surveys reported a significant underdensity of galaxies, consistent with a huge void. Others found a less pronounced deficit. The results have been mixed, but the supervoid hypothesis remains viable. It is not supernatural. It is a natural consequence of large-scale structure and the influence of dark energy. The cold spot is not a crack in the cosmic egg. It is a window into the enormous empties that pepper the universe. Now, let us delve deeper into the concept of time dilation when traveling across void distances. The distances we are talking about are almost incomprehensible. A typical void is 30 million light-years across. Even at the speed of light, traveling from one side to the other would take 30 million years. But our spacecraft cannot reach the speed of light. If we could somehow accelerate to 99.9% of the speed of light, time dilation would work in our favor, or against us, depending on perspective. From the point of view of an observer on Earth, the journey would take slightly more than 30 million years. But for the astronauts on board, due to relativistic time dilation, the trip would last only a fraction of that time. At 99.9% of C, the time dilation factor is about 22. So the crew would experience about 1.36 million years of subjective time to cross that 30 million light-year void. That is still an incomprehensible duration, but it is shorter than the external time. If we could push to 99.999% of C, the dilation factor jumps to about 224, and the subjective time drops to about 134,000 years, still far beyond a human lifetime. But if we consider an even larger void, like the Booty's void at 300 million light-years, the numbers become even more staggering. To cross that distance at 99.999% of C, the crew would experience over 1 million years. The point is that even with extreme time dilation, the sheer scale of these voids makes interstellar, let alone intergalactic, travel virtually impossible for biological beings. Time dilation is not a magic bypass. It merely compresses an already astronomical timescale into a still astronomical one. But time dilation also affects how we observe galaxies inside voids. Light from those 60 isolated galaxies in the Booty's void has taken hundreds of millions of years to reach us. We see them as they were hundreds of millions of years ago. Because the void is expanding, the light is redshifted, and the redshift tells us their distance and the expansion rate. Interestingly, if a civilization evolved inside one of those void galaxies, they would observe a very different universe. The cosmic expansion would appear to be faster because the void itself expands more rapidly than the average. Their measurement of the Hubble constant would be biased high. They might conclude that the universe is younger than it actually is, and because there are so few galaxies to study, their cosmology would be based on very sparse data. It would take them much longer to figure out the existence of dark energy. They might even develop a different theory of gravity to explain the apparent emptiness around them. This is a humbling thought. Our own understanding of the universe is shaped by the fact that we live in a moderately dense region surrounded by a rich web of galaxies. If we lived in a deep void, our cosmic perspective would be radically different. Now, let us consider a more extreme scenario. What if Earth itself were not just inside a mild void like the KBC, but deep inside a supervoid with a diameter of, say, 2 billion light-years? The implications for life would be profound. First, the density of matter around us would be so low that the formation of structures like our solar system might have been impossible. Voids are born from the same initial fluctuations that created galaxies, but in a void, the density is too low for gas clouds to collapse efficiently into stars and planets. The Boots void, for instance, contains only 60 galaxies, but those galaxies did form. So small pockets of higher density do exist inside voids, and they can host planets. However, those galaxies are old and isolated. If Earth were in such a galaxy, the night sky would be almost completely devoid of other galaxies. That would have consequences for the history of science. Without the Andromeda Galaxy visible to the naked eye, something that is easily seen from dark locations on Earth, early astronomers would have no evidence that the universe extended beyond the Milky Way. The Copernican revolution might be delayed by centuries. The concept of an expanding universe might never be discovered until far later, because there would be no nearby galaxies to measure redshifts. The cosmic microwave background would still be detectable, but its dipole, the slight temperature difference caused by our motion through the universe, would also be different because our motion relative to the CMB would be influenced by the large-scale flows around the void. It is entirely possible that a civilization inside a deep void would never develop a theory of the Big Bang until they had built telescopes capable of detecting extremely faint, distant galaxies on the void's boundary. Science would progress in a different direction, but perhaps the most significant implication of living inside a void is the effect on our measurements of the expansion rate of the universe. As mentioned, the KBC void biases our local measurement of the Hubble constant. This tension, known as the Hubble constant problem or Hubble tension, is one of the hottest topics in cosmology. The value measured from nearby supernovae and Cepheid variables is about 73 kilometers per second per megaparsec, while the value inferred from the cosmic microwave background is about 67. The difference is small, but statistically significant, and it may be due to our position in a void. If we lived in a deeper void, the discrepancy would be even larger. In fact, some cosmologists have proposed that the Hubble tension might be entirely explained by a local void that is larger and emptier than the KBC. If that is the case, then the universe's true expansion rate is the one from the CMB, and our local measurement is biased. This is a beautiful example of how our cosmic address, even on the largest scales, affects our view of reality. Now, let us turn to the future. Voids are not static. They grow as the universe expands. Over the next tens of billions of years, the voids will become even larger and emptier. The galaxies within the walls and filaments will continue to merge, forming ever more massive clusters, but the voids between them will stretch, and the galaxies inside voids, which are few and far between, will become increasingly isolated. In the far future, after trillions of years, the accelerating expansion will have pushed everything beyond our local gravitationally bound group out of sight. Each galaxy will sit alone in its own Hubble volume, surrounded by a void that stretches to the cosmic horizon. The universe will become a collection of isolated islands of stars, each one at the center of its own immense void. Eventually, even those stars will burn out, and matter will decay into radiation and black holes, which will then evaporate. The universe will approach a state of maximum entropy, a cold, dark, uniform exchange. At that point, the distinction between void and structure will vanish. The entire cosmos will be one colossal void, as empty as the spaces between galaxies are today. But for now, voids remain one of the most fascinating and underappreciated components of the universe. They are not just empty. They are active participants in cosmic evolution. They shape the motion of galaxies. They imprint on the cosmic microwave background. They test our theories of dark energy, and they remind us that the universe is not a uniform soup, but a complex, sponge-like network of matter and void. The next time you look up at a clear night sky and see the Milky Way stretching overhead, consider that the darkness between the stars is not just the absence of light. It is a gateway to the vast emptiness that fills most of the universe. And somewhere out there, in one of those million light-year wide voids, there may be a lone galaxy with a planet where a civilization is gazing at a sky that holds only a single smudge of light, their own galaxy, and wondering if they are alone. They are. In the most profound sense, we all live in a void. It is just a matter of scale. But what does the history of void discovery tell us about how we came to understand these colossal emptinesses? Let us travel back to the 1970s, a decade when astronomy was undergoing a quiet revolution. Redshift surveys, the systematic measurement of how fast galaxies are moving away from us, were beginning to reveal the universe in 3 dimensions for the first time. Before then, our picture of the cosmos was essentially a flat map. We knew where galaxies were on the sky, but we had no idea of their depth. The first hints of voids emerged when astronomers noticed that certain patches of sky seemed to contain far fewer galaxies than expected, even after accounting for obscuring dust. In 1977, a team led by Stephen Gregory and Laird Thompson studied the region around the Coma cluster, one of the richest galaxy clusters in the nearby universe. They found that the density of galaxies in front of the cluster dropped dramatically, as if there were a bubble of emptiness stretching for tens of millions of light-years. This was one of the first tentative identifications of a void. But the real breakthrough came in 1981, when a team of astronomers using the Kitt Peak National Observatory's 4-meter telescope announced the discovery of an enormous void in the direction of the constellation Bootes. The Bootes void, as it became known, was estimated to be between 250 and 330 million light-years in diameter. At the time, this was shocking. Standard models of galaxy formation predicted that voids of that size should not exist. There simply hadn't been enough time since the Big Bang for gravity to empty out such a vast region. The discoverers, led by Robert Kirshner, initially called it a great hole and speculated that it might be a statistical fluke. But subsequent surveys confirmed it. The Bootes void was real, and it contained only a handful of galaxies, perhaps 60, where thousands were expected. The void's existence forced cosmologists to rethink how large-scale structure forms. It was a clue that the universe's initial density fluctuations were far more extreme than previously imagined, and that voids could grow to enormous sizes through the interplay of dark matter and dark energy. The Bootes void also earned a nickname that stuck, the Great Nothing, and it became a focal point for for philosophical speculation. What would it be like to live inside such a void? As we discussed earlier, if humanity had evolved in one of those 60 isolated galaxies, our view of the cosmos would be radically impoverished. But let us delve deeper into that scenario. Imagine a civilization on a planet orbiting a star in the Bootes void. Their night sky would be almost completely black. The Milky Way, their own galaxy, would appear as a faint, elongated smudge, but there would be no Andromeda, no Magellanic Clouds, no recognizable constellations of external galaxies. For thousands of years, their astronomers would believe that their galaxy was the entire universe. They might develop a geocentric or heliocentric model, but they would have no evidence that other galaxies exist. The concept of an expanding universe would be impossible to formulate because there would be no distant objects to show redshift. Their cosmic microwave background would still be detectable, but it would appear incredibly uniform. The anisotropies caused by large-scale structure would be much smaller because the void's density fluctuations are suppressed. They might conclude that the universe is static and unchanging. Only when they developed extremely sensitive telescopes capable of detecting the faint, highly redshifted light of galaxies at the void's boundary, galaxies that are hundreds of millions of light-years away, would they begin to suspect that they are not alone. And even then, the redshift of those boundary galaxies would be so extreme that they might misinterpret it as a property of the galaxies themselves rather than cosmic expansion. This thought experiment is not just idle musing. It has real implications for our own cosmological biases. We live in the KBC void, a region of space about 2 billion light-years across that has a galaxy density roughly 20% lower than the cosmic average. That may not sound like much, but it is enough to cause a measurable bias in our local measurement of the Hubble constant. In fact, the KBC void was first proposed in 2013 by a team led by Ryan Keenan, and it has since been refined by other studies. The void is centered relatively close to us. We are within about 200 million light-years of its center, and it extends to include the entire Laniakea supercluster, which contains the Milky Way, the Local Group, the Virgo cluster, and many other structures. So, we are not in a deep, empty void. We are in a modest underdensity. But the effect is real. The gravity of the denser surrounding walls pulls us slightly toward them, giving our local group a peculiar velocity of about 600 kilometers per second relative to the cosmic microwave background. This peculiar velocity alters the measured redshifts of nearby galaxies, and if not accounted for, it leads to an overestimate of the local expansion rate. Hence, the Hubble tension. Measurements from supernovae and Cepheid variables give a value of around 73 mpc, while the CMB gives 67.44 mpc. The difference is about 8%, which is too large to be explained by measurement error. Some cosmologists argue that the entire tension could be resolved if our local void is larger and emptier than currently thought. In other words, the Hubble constant problem might be a signature of our position in the cosmic web. This brings us to a crucial point. Voids are not just passive empty spaces. They are active agents that shape the large-scale velocity field. Galaxies move toward the densest regions, draining the voids. Over billions of years, this flow leaves voids increasingly empty, while the walls become denser and more clustered. The process is analogous to the formation of soap bubbles. The bubbles grow as gas pushes out from the interior, leaving thin films of liquid between them. In the cosmic web, voids are the bubbles, and filaments are the films. And just as soap bubbles can merge, so too can voids. The Bootes void is thought to be the result of two smaller voids merging, leaving a nearly spherical shape and a tube of remnant galaxies at its center. This merger process is ongoing. As the universe expands, voids of all sizes continue to grow, and occasionally, when two voids expand into each other, their boundaries collapse into a single larger void. This is how the largest supervoids form. Now, let us turn to the discovery of those supervoids. In the 1990s, the Las Campanas Redshift Survey mapped 26,000 galaxies and revealed a network of voids and walls spanning hundreds of millions of light-years. Then came the Sloan Digital Sky Survey, which by the 2000s had cataloged over 1 million galaxies. This data allowed astronomers to identify voids statistically. One of the largest voids found by SDSS is the Hercules supercluster void, also known as the Great Wall Void, which lies on the edge of the Hercules supercluster. It measures about 300 million light-years across. But even that is dwarfed by the giant void, discovered in 2001 in the constellation Canes Venatici. That void is about 1.3 billion light-years in diameter, making it one of the largest known structures of any kind. And yet, it is still not the largest void by definition. The KBC void, as we said, is about 2 billion light-years in diameter, but it is not totally empty. It contains our own supercluster. So, the record for the largest truly empty void might belong to something else. In 2015, a team led by Istvan Sapudi used data from the Pan-STARRS telescope and the Wide-Field Infrared Survey Explorer to identify a possible supervoid in the direction of the CMB cold spot. They found a region with a significant deficit of galaxies, about 1.8 billion light-years across. This candidate supervoid, if confirmed, would be the largest single void ever detected, and it would be aligned almost perfectly with the cold spot. The integrated Sachs-Wolf effect from such a void could produce the observed temperature anomaly. However, subsequent surveys by the Dark Energy Survey and the VISTA telescope found a less pronounced deficit, leaving the matter unresolved. The Eridanus supervoid, as it is sometimes called, remains a tantalizing possibility. Future surveys like the Euclid telescope, launched in 2023, and the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map hundreds of millions of galaxies across vast volumes. They will be able to confirm or refute the supervoid hypothesis by measuring the galaxy density and the gravitational lensing signal around the cold spot. But even if the cold spot is not caused by a supervoid, the search has taught us something valuable. Voids can be used as cosmic test beds for dark energy. The integrated Sachs-Wolf effect is sensitive to the growth rate of voids, which in turn depends on the amount of dark energy in the universe. By stacking the CMB signals from thousands of known voids, astronomers have measured a subtle but statistically significant ISW effect, consistent with the standard Lambda-CDM model, where dark energy makes up about 70% of the energy density. You might think you know what a planet is. You've seen pictures of Earth from space, blue oceans, white clouds, green continents. You know about Mars, the red desert, Saturn with its rings, Jupiter's great red spot. These worlds feel familiar, even the ones we've never visited. But the universe has a cruel sense of humor. For every calm, stable world like ours, there are hundreds of nightmares out there, orbiting distant stars that would shred any notion of safety you've ever had. Planets where the atmosphere is made of vaporized rock, where it rains glass sideways at thousands of miles per hour, where the surface is hotter than the surface of a star, where entire worlds are being eaten alive by their own suns. And the most unsettling part? We've already found them. There are more being discovered every year, and every single one of them forces us to ask the same question. How did we get so lucky? Because if you look at the full catalog of exoplanets, the thousands of worlds we've confirmed beyond our solar system, you realize that Earth isn't the norm. It's the exception, the rare, fragile, precious exception. And the more we learn about these terrifying planets, the more we understand just how extraordinary our home really is. But before we dive into the deep end, let's talk about something you've probably noticed. The names of these planets: YT9733b, Kelt 9b, Wasp 12b, Gliese 486b. They don't exactly roll off the tongue. There's a method to this madness. The first part is usually the name of the star the planet orbits. HD stands for Henry Draper Catalog, a star catalog from the early 20th century. Kelt comes from the Kilo-Degree Extremely Little Telescope Survey. WASP is the wide-angle search for planets. Gliese is a catalog of nearby stars. And the lowercase letter BCD indicates the order of discovery around that star. The first planet discovered gets a B, the second gets C, and so on. The star itself is A. So when you hear HD 189733b, it means the first planet found orbiting the star HD 189733. It's a system that makes sense to astronomers, even if it sounds like a license plate to everyone else. Now that you've got that sorted, let's enter a world where the weather forecast reads like a horror movie. Imagine you're standing on the surface of a planet 63 light-years from Earth. The star in the sky is huge. It fills a quarter of the sky, blazing with a fierce orange light. But you don't have much time to admire it, because the wind is picking up. Not a gentle breeze, not even a hurricane. We're talking 4,500 miles per hour. That's faster than most fighter jets, faster than a speeding bullet. And carried in that wind are tiny particles of glass, microscopic shards of silicate, the same stuff that makes up sand and windows. On the day side of this planet, the temperature is nearly 1,700 degrees Fahrenheit, hot enough to melt lead, hot enough to vaporize rock. The silicates there exist as a vapor, invisible like steam. But as that vapor gets swept toward the night side, where it's 1,000 degrees cooler, it condenses. It forms tiny droplets of liquid glass, which then freeze into solid particles. And because the wind is moving at thousands of miles per hour, these particles aren't falling straight down. They're flying horizontally. Sideways rain, glass rain. Each particle is tiny, but at that speed, each one carries the energy of a bullet. You'd be sandblasted to nothing in seconds. This is HD 189733b, a gas giant about the same mass as Jupiter, but orbiting so close to its star that a year lasts just over 2 Earth days. It's what astronomers call a hot Jupiter. And hot Jupiters were the first big shock to our understanding of planetary systems. Before 1995, we only knew the planets in our own solar system, and they seemed to follow a logical pattern. Small, rocky worlds close to the Sun. Mercury, Venus, Earth, Mars, giant gas planets far away, Jupiter, Saturn, Uranus, Neptune. We assumed all planetary systems worked the same way. Rocky planets form close to the star because only heavy materials can survive the heat. Gas giants form far out where it's cold enough for ices and gases to clump together. It made perfect sense. And then, in October 1995, astronomers Michel Mayor and Didier Queloz announced something that shattered that picture. They had been monitoring a star called 51 Pegasi, about 50 light-years away. Using a technique called radial velocity, measuring the tiny wobble in a star's motion caused by an orbiting planet, they found a signal that repeated every 4.2 days, a planet orbiting its star in just over 4 days. That was impossibly close. Mercury, the closest planet in our solar system, takes 88 days. A 4-day orbit meant the planet was almost 8 times closer to its star than Mercury is to our Sun. At that distance, the temperature would be around 1,800 degrees Fahrenheit. A gas giant couldn't possibly form there. The heat would prevent it. Yet there it was. Mayor and Queloz had found the first exoplanet around a Sun-like star. They called it 51 Pegasi b, and they had no idea how it got there. The answer, we now know, is planetary migration. Planets don't always stay where they form. When a young planet is still embedded in the disk of gas and dust that surrounds a new star, that disk can act like a brake. The planet experiences drag, loses orbital energy, and slowly spirals inward. Over millions of years, a gas giant that formed in the cold outer regions can end up right next to its star. It crosses the orbits of any rocky planets that might have been there, either ejecting them or swallowing them whole. The system gets completely reshuffled, and the planet ends up in a scorching close-in orbit, where it will spend the rest of its existence being baked alive. 51 Pegasi b was just the first. Since then, we've found hundreds of hot Jupiters. They're not rare. In fact, about 1% of Sun-like stars have one. That's billions of these worlds in our galaxy alone, and some of them are far more extreme than the first. Take Kelt 9b. This planet orbits a star that is itself a monster, an A-type star with a surface temperature of 18,000 degrees Fahrenheit, more than 3 times hotter than our Sun. Kelt 9b circles this blazing cauldron at a distance of only 4 million miles. That's 9 times closer than Mercury is to our Sun. The orbital period is 1.5 days. The planet is moving so fast, it takes only 36 hours to complete a year. And the results are catastrophic. The dayside temperature of Kelt 9b is estimated at 7,800 degrees Fahrenheit. That's nearly as hot as the surface of the Sun itself. At those temperatures, molecules can't hold together. Water is torn apart into hydrogen and oxygen atoms. Carbon dioxide splits into carbon and oxygen. Even heavier elements like iron and titanium exist as vapor. The atmosphere isn't made of gas in the normal sense. It's a plasma of individual atoms. Scientists have detected iron, titanium, sodium, magnesium, all floating in a superheated broth. And because the planet is tidally locked, one side always facing the star, the temperature difference between the day side and night side is thousands of degrees. That drives winds of unimaginable violence, probably exceeding 5,000 miles per hour. But none of that is the scariest part. The scariest part is that Kelt 9b is dying. Right now, the intense ultraviolet radiation from its star is literally tearing the planet's atmosphere away. Every second, Kelt 9b loses millions of tons of gas into space. hydrogen escapes fastest, but heavier atoms are going too. Scientists have detected a massive cloud of escaping material around the planet, trailing behind it like a comet's tail. Within a few million years, a blink in cosmic time, the planet's atmosphere will be completely stripped away. What's left might be a bare rocky core, or the planet might spiral further in and be torn apart by tidal forces. Either way, Kelt 9b has no future. We are watching a world evaporate in real time. And then there's WASP 12b, a planet being eaten alive in a slightly different way. This gas giant orbits its star at a distance of only 2 million miles, so close that a year lasts just 1.1 Earth days. The dayside temperature is around 4,500 degrees Fahrenheit. But the real terror here is tidal forces. When a planet orbits that close, the star's gravity pulls much harder on the near side than the far side. The planet gets stretched into an egg shape, or even a teardrop. The constant flexing generates heat inside the planet, puffing it up to nearly twice the size of Jupiter. And that makes it even easier for the atmosphere to escape. WASP 12b is losing about 6 billion tons of material every second. That's the equivalent of Earth's entire atmosphere every 26 million years. The lost gas doesn't just vanish, it forms a disk around the star, and the star slowly devours it. Scientists have detected unusually high levels of carbon in the star's spectrum, pollution from the planet. In about 10 million years, WASP 12b as we know it will be gone. The star will have consumed it, atom by atom. But hot Jupiters aren't the only nightmare worlds. There are lava planets, worlds where the surface isn't just hot, it's molten. Take K2-0141b, a super-Earth about 200 light-years away. It's roughly 1.5 times the size of Earth and about 5 times its mass. But it orbits its star at a distance of only 1.6 million miles, 22 times closer than Mercury. A year on K2-0141b lasts just 9 hours. The dayside temperature is estimated at 4,500 degrees Fahrenheit. That's hot enough to melt rock. Not just melt it, vaporize it. The entire dayside of this planet is probably covered in an ocean of molten lava hundreds of miles deep. Convection currents churn the magma. Waves of liquid rock crash against any solid features that might exist. And the atmosphere is filled with vaporized silicates, rock gas. As this vapor rises and cools slightly, it can condense into tiny droplets of liquid rock, which then fall back to the surface as rock rain. Not water rain, rock rain. On the night side, which is permanently dark, temperatures drop to around 2,000 degrees Fahrenheit, still hot enough to melt many minerals, but cool enough that the lava ocean solidifies at the boundary. There's a shoreline where liquid rock meets solid rock, constantly shifting as winds push hot gas across the terminator. If you could stand there, and you cannot, you'd see waves of glowing stone lapping against a shore of black basalt. And here's the thing. Earth was once a lava planet. About 4.5 billion years ago, after a Mars-sized object named Theia slammed into our young world, the entire surface was molten for millions of years. We had an ocean of magma. We had a sky filled with vaporized rock. But we were far enough from the sun that we eventually cooled down. The crust solidified. Water vapor condensed into oceans. Life emerged. K2-141b never got that chance. It's stuck in that primordial hell forever because it's too close to its star to ever cool. But perhaps the most unsettling planets of all are the ones that orbit dead stars. PSR B1829-10 is a pulsar, the collapsed core of a massive star that went supernova. When a star much larger than our Sun runs out of fuel, its core collapses into a neutron star just a dozen miles across. A teaspoon of its material would weigh 1 billion tons. The explosion that created it, a supernova, would have vaporized any planets that were orbiting the original star. Nothing should survive. Yet in 1991, astronomers detected a planet orbiting this pulsar. How? The pulsar spins 317 times a minute, emitting beams of radiation like a lighthouse. The pulses are incredibly regular, more regular than any clock. But tiny variations in the arrival times revealed a wobble, the gravitational tug of a planet. PSR B1829-10b is about 4 times the mass of Earth. It orbits the pulsar at roughly the same distance as the asteroid belt from our Sun, but it formed after the supernova from the debris that fell back and coalesced. These are called zombie planets, worlds that rose from the death of a star, and the environment is unimaginably hostile. The pulsar emits intense beams of X-rays and gamma rays. If you stood on the surface of that planet, you'd be bathed in radiation 317 times every minute. The dose would be millions of times higher than what's lethal on Earth. It would shred your DNA, destroy any organic molecules, strip away any atmosphere. The planet is a barren, sterilized rock orbiting a corpse of a star, and it will remain that way forever. Then there are the rogue planets, worlds that don't orbit any star at all. They drift through interstellar space alone. CFBDSIR 2140723 is one such orphan. It's a gas giant 4 to 7 times the mass of Jupiter, about 100 light-years away. It's still hot from its formation, around 750 degrees Fahrenheit, but that heat is slowly bleeding away. There is no sun to warm it. The sky is completely black. The Milky Way shines as a faint band, but none of those stars are close enough to provide any warmth. Eventually, over billions of years, this planet will cool to near absolute zero. Its atmosphere might freeze and fall as ammonia snow. The planet will become a dark, frozen, silent world drifting through the void forever. And here's the terrifying part. Rogue planets might be incredibly common. Some estimates suggest there could be billions of them in our galaxy alone, maybe even more than planets that orbit stars. They form when gravitational interactions eject planets from their systems, or when gas clouds collapse into objects too small to become stars. We can't see most of them. They're dark and cold. They're out there right now, passing through interstellar space unnoticed. The galaxy might be filled with these frozen wanderers, and we would never know. But the most common type of exoplanet we've discovered is something we don't even have in our solar system: super-Earths. These are planets with masses between 1 and 10 times that of Earth. They dominate the exoplanet catalog, and they're profoundly alien. Take Gliese 486b. It orbits a red dwarf star 26 light-years away. The planet is about 3 times Earth's mass and 1.3 times its radius, so it's probably rocky. But its year lasts 1.47 days. It's tidally locked, with a dayside temperature of 850 degrees Fahrenheit. Any water on that planet wouldn't be liquid or gas. It would be supercritical. Above a certain temperature and pressure, the distinction between liquid and gas disappears. Water becomes a supercritical fluid that can dissolve materials normal water can't. It's chemically aggressive. You couldn't survive in it. You couldn't even build a suit to withstand it. And many super-Earths have conditions like this: high temperature, high pressure, exotic states of matter we barely understand on Earth. Then there's 55 Cancri e, about 40 light-years away. It's 8 times Earth's mass, twice Earth's diameter, and orbits its star every 18 hours. The surface temperature is 3,600 degrees Fahrenheit. Based on its density, some models suggest it could have a thick layer of diamond beneath its surface, a planet where a third of the mass might be carbon in the form of diamond. The idea is still debated, but it shows how wildly different these worlds can be. They're not just bigger versions of Earth, they're entirely new categories of planet. And what about planets in the habitable zone, that Goldilocks region where liquid water could theoretically exist? The TRAPPIST-1 system, 40 light-years away, has 7 Earth-sized planets. 3 of them orbit in the habitable zone of the red dwarf star. TRAPPIST-1e, for example, receives about the same amount of light as Earth. Its estimated surface temperature might be around 30 degrees Fahrenheit. On paper, it sounds promising, but there are problems. The planet is almost certainly tidally locked. One side always day, one side always night. The only potentially habitable strip is the terminator, the narrow band where the sun sits permanently on the horizon. But red dwarfs are violent. They produce frequent flares that bathe their planets in X-rays and ultraviolet light. TRAPPIST-1 is known to flare regularly. Any life on such a planet would need to hide underground or develop extreme radiation resistance. The atmosphere might be stripped away over billions of years, so even a planet in the habitable zone can be far from habitable. Then there are planets with orbits so eccentric they defy imagination. HD 80606b is a gas giant 4 times the mass of Jupiter. Its orbit is almost a straight line, an eccentricity of 0.933. At its closest approach to the star, it's only 2.8 million miles away, closer than Mercury. At its farthest, it's 79 million miles away, nearly the distance of Venus from our Sun. Every 111 days, the planet swings from being scorched at several thousand degrees to being relatively cold, then back again. The atmosphere boils, freezes, boils again. Tidal forces during close approach flex the planet so violently that it generates immense internal heat. This world never reaches equilibrium. It's constantly in a state of violent transition. So why do all these terrifying planets exist? Because planetary systems are chaotic. Most of them experience migration, scattering, collisions. Most planets don't stay where they form. They get tossed around, shoved into extreme orbits, ejected entirely. Our own solar system is the exception. We have a stable arrangement that has persisted for billions of years. Jupiter stayed in the outer system instead of migrating inward. Earth stayed in its circular orbit. We have a large moon that stabilizes our axial tilt. We have plate tectonics that regulate our climate. We have a magnetic field that protects our atmosphere from being stripped away by the solar wind. We have a star that is calm and steady, not a violent red dwarf or a short-lived blue giant. All of these factors, and many more, had to align perfectly for Earth to be the life-supporting world it is. And they did align. But the default in the universe seems to be chaos. The default is extreme conditions. The default is a planet where glass rains sideways, or where molten rock oceans churn under a sky of vaporized metal, or where a dead star's radiation sterilizes every inch of a world that rose from its own ashes. The exoplanets we've discovered are not oddities. They're the norm. Earth is the oddity, and that's a humbling thought. Every time we look up at the night sky, we're looking at billions of stars, and around most of them, there are planets. But the vast majority of those planets are places you would never want to visit. They're nightmares. They're hostile. They're spectacularly beautiful in their extremity, but they are utterly lifeless. And that makes the calm, blue, living world we call home infinitely more precious. We're just beginning to explore this vast menagerie of terrifying worlds. The James Webb Space Telescope is already studying the atmospheres of exoplanets, detecting water, carbon dioxide, and sulfur dioxide. Future telescopes, like the Nancy Grace Roman Space Telescope, will find thousands more, including cold planets and rogue worlds. We might one day find a planet with biosignatures, oxygen and methane together in an atmosphere that could only be produced by life. But until then, every new discovery reminds us of how special Earth truly is. So the next time you step outside and feel a gentle breeze, or watch a rainstorm, or see the sun rise and set on a predictable schedule, remember the planets we've talked about. Remember the glass rain. Remember the lava oceans. Remember the worlds being eaten alive. And be grateful that you live on the one planet that got it all right. Because out there, in the darkness between the stars, the universe is full of nightmares. And we are the lucky ones. But the cosmic horror show doesn't end there. Every new telescope reveals more worlds that push the boundaries of what we thought possible. And before we dive deeper, let's take a moment to understand how these planets get their names. Because the naming conventions themselves tell a story of discovery. Most exoplanet names come from the survey or telescope that found them. HD stands for the Henry Draper Catalog, a star catalog from the early 20th century. KELT is the kilodegree extremely little telescope. WASP is the wide-angle search for planets. Kepler planets come from the Kepler Space Telescope. TRAPPIST is the transiting planets and planetesimals small telescope. The letter after the star name, like B in HD 189733b, indicates the order of discovery. The first planet found around that star gets B, the second gets C, and so on. So when you see a name like K2141b, it means the first planet discovered around star K2141, found during the second phase of the Kepler mission. These labels are cold and scientific, but they hide terrifying worlds behind their dry nomenclature. Let me tell you about a planet that might be even stranger than any we've discussed. Kepler 70b. This world orbits a star that has already gone through its red giant phase. The star, Kepler 70, is now a white dwarf, the hot, dense core left behind after a sun-like star blows off its outer layers. Kepler 70b orbits this stellar corpse at a distance of only about 250,000 miles. That's closer than the Moon is to Earth. The orbital period is just 5.8 hours. A year on this planet is shorter than a work shift. The surface temperature is estimated at over 7,000 degrees Fahrenheit, hotter than the surface of many stars. But what makes Kepler 70b truly terrifying is its history. When the star expanded into a red giant, it would have engulfed any planets orbiting nearby. Kepler 70b must have been inside the star itself, orbiting through the star's outer layers, being dragged through plasma at stellar temperatures. The planet somehow survived, It's a charred, baked, compact world, likely a rocky remnant, stripped of any atmosphere, its surface melted and re-solidified. This is a planet that passed through a star and lived to tell the tale. It's a testament to the resilience of matter, but also a reminder of the violence that stars can unleash on their own children. Now consider the planet known as GJ367b. It's a super-Mercury, a world with a massive iron core, about half of its total mass. It orbits a red dwarf star just 31 light-years away. The planet is roughly the size of Mars, but it's incredibly dense, suggesting it's the stripped core of a larger world that had its rocky mantle torn away, perhaps by a giant impact or by the star itself. The dayside temperature is around 2,700 degrees Fahrenheit. A year on GJ367b lasts just 7.7 hours. Imagine a world where the sun rises and sets every few hours, where the surface is a vast iron plain, where the gravity is crushing, and where any atmosphere that might have existed was lost eons ago. This planet is a skeleton, the innermost core of a world that was vivisected by cosmic forces. And then there are the planets that defy classification altogether. Some exoplanets have densities so low they've been called puffy planets. Take WASP-17b. It's a gas giant about half the mass of Jupiter but nearly twice its radius, so puffed up that its average density is less than that of Cork. It would float on water if you could find an ocean big enough. But don't let that buoyant image fool you. WASP-17b orbits its star in just 3.7 days, and the extreme heat causes its atmosphere to expand like a balloon. The planet rotates in the opposite direction of its star, a retrograde orbit, suggesting it experienced a violent scattering event in its past. The atmosphere is filled with sodium and potassium, and the temperature swings between its day and night sides are vast. The planet's bloated state means its gravity is weak at the cloud tops, so the upper atmosphere is slowly bleeding away. It's a world that's literally inflating itself to death. We also have planets where the weather is not just violent, but chemically exotic. Consider the carbon planet scenario. On Earth, the crust is rich in oxygen and silicon, forming silicates. But if a planet forms in a region with more carbon than oxygen, the chemistry flips. Instead of quartz and granite, the surface might be covered in graphite or diamond. The atmosphere could be thick with carbon monoxide and methane. Rain might be made of tar or liquid hydrocarbons. A carbon planet would be a dark, oily, sooty world, like a cosmic coal mine. We haven't definitively found one yet, but models suggest they should exist around carbon-rich stars. And if such a planet happened to have intelligent life, they would breathe carbon compounds and drink liquid methane. The very biochemistry would be alien, and yet even that is just one possibility in an almost infinite parameter space. Let's talk about the conditions for life more directly. Life as we know it requires liquid water, a source of energy, and a stable environment over geological timescales. It needs a planetary surface with moderate temperatures, an atmosphere that provides pressure and protection, and a magnetic field to shield against cosmic radiation. It needs a star that doesn't flare too frequently, and an orbit that doesn't swing from scorching to freezing. It needs plate tectonics to recycle carbon and regulate climate. It needs a large moon to stabilize the axial tilt, or some other mechanism. It needs the right amount of water, not too much, not too little. It needs a history without catastrophic supernovae or gamma-ray bursts nearby. The list of requirements is long, and the universe seems designed to break most of them. The terrifying planets we've explored are not just extreme, they are the statistical norm. Most planets will fail at least one, if not many, of these requirements. That's why Earth feels so perfect, because it's the rare cosmic lottery winner. But we should not mistake terrifying for devoid of wonder. These nightmare worlds are beautiful in their own right. The glass rain of HD 189733b is a stunning example of planetary physics in action, a global-scale weather system that turns silicon into shrapnel. The lava ocean of K2-14E1b is a glimpse into Earth's own violent past. The doomed atmosphere of Kelt 9b is a dramatic spectacle of a world fighting against evaporation. The zombie planet around the pulsar is a story of rebirth from death. Each of these planets is a natural laboratory that teaches us something profound about the universe's capacity for creation and destruction. And there are even more exoplanet oddities we haven't touched on. Planets with rings so large they would dominate the sky. Planets where it rains rubies and sapphires. Planets that are literally being ripped apart by their own rotation. Planets that orbit binary stars, experiencing twin sunships that would be beautiful, but the orbits are often unstable. Planets that are so old they've had billions of years to cool, yet still harbor internal heat from radioactive decay. Some of these worlds might have subsurface oceans kept liquid by tidal heating, like Jupiter's moon Europa. But on a planetary scale, could life exist in those dark oceans, under miles of ice, warmed by no star? Possibly. But that life would be isolated, trapped in a frozen shell, never seeing the light of a sun. It's a different kind of terror. The terror of eternal darkness, of a world where the surface is a sterile desert of ice and rock, and all the action is hidden beneath. As we push the frontiers of exoplanet science, we're also learning that our own solar system might be more unusual than we ever imagined. The arrangement of planets, small rocky inner worlds, then a gap, then giant outer worlds, is not the typical pattern. Most systems have super-Earths in close orbits. Many have multiple planets packed tightly together, like TRAPPIST-1. Others have eccentric giants that disrupt everything. Our solar system's quiet stability is a product of luck and timing. If Jupiter had migrated inward just a little more, it would have scattered the inner planets. If the asteroid belt had been more massive, impacts would have been catastrophic. If the moon hadn't formed, Earth's tilt would have wobbled chaotically. Every detail of our existence is contingent on a cascade of improbable events. So what does this mean for our search for life? It means we should not expect to find a second Earth soon. The nearest truly Earth-like world might be hundreds of light years away. It might have a different atmosphere, a different day length, a different geological history. It might be habitable for microbes, but not for complex life. Or it might be completely sterile, lacking some key ingredient. But the search itself is valuable. Each new exoplanet discovery adds another data point to our understanding of planetary formation and evolution. And even if we never find another living world, the knowledge that Earth is so extraordinarily rare can give us a profound sense of responsibility. This planet, our planet, is a fragile oasis in a universe of fire and ice. We have the power to preserve it or to destroy it. Think about that the next time you hear about a politician denying climate change, or a corporation polluting a river, or a war that destroys ecosystems. Earth is not just our home. It is the only known shelter for life in the entire cosmic desert. The planets we've explored tonight, the ones with glass rains and molten oceans and evaporating atmospheres, they are the rule. Earth is the exception, and we are the custodians of that exception. We are the ones who can appreciate the beauty of a sunrise, the sound of rain, the feeling of wind on our skin. Those simple, everyday experiences are not guaranteed anywhere else in the universe, as far as we know. They are miracles, wrapped in improbable physics, supported by billions of years of stable conditions. As our telescopes get better, as we discover more strange and terrifying worlds, let that knowledge deepen your wonder, not your fear. The universe is vast and hostile, but it also contains the narrow, precious window that allowed us to exist. And in that window, we have the chance to learn, to explore, and to cherish the pale blue dot that carries everything we have ever loved. So, go outside tonight, if you can. Look up at the stars. Remember that each one might host a planet where the sky is filled with flying glass, where the ground is liquid rock, where the air is being torn away into the void. And then look at your own hands. Feel the air in your lungs. Appreciate the ground beneath your feet. You are standing on the rarest, most extraordinary world in the known universe, and you, right now, are alive to witness it. That is the greatest wonder of all. You feel it, don't you? That quiet hum in the back of your mind when you look up at the night sky. It's not fear. It's not wonder. It's something in between. It's the feeling that you're standing at the edge of a vast, silent room, and you're not quite sure if anyone else is in there with you, or if they've already left, or if they ever came at all. That feeling has a name, or at least a label we stick on it to make it manageable. The Fermi paradox, the contradiction between the high probability of extraterrestrial life based on the sheer scale of the universe and the complete lack of evidence for it. It's a tidy little package for a very messy, very unsettling idea. But here's the thing about the Fermi paradox that people usually get wrong. They frame it as a binary. Either the cosmos is teeming with company and we just haven't bumped into them yet, or the cosmos is empty and we are utterly, terrifyingly alone. Those are the two poles we argue about, the crowded universe versus the lonely one. But there's a third door, a door we don't open very often because what's behind it isn't comfortable. It's the possibility that the universe isn't empty, and it isn't full. It's full of ghosts. It's the possibility that the silence we hear isn't the silence of a place where nothing ever happened. It's the silence of a place where things happened and then stop. A library where the books are still on the shelves, but the readers have all gone home. The lights are off, the stories are still there, the voices aren't. This isn't about whether life can start. We have pretty good evidence that it can, because it did, here. The harder question, the one we are only beginning to understand, is whether life can last. The universe, as far as we can currently see it, contains a confirmed inventory of just over 6,000 worlds beyond our solar system. That's the official count, and a credible estimate of hundreds of billions more in our galaxy alone. The natural assumption, the one we lean on when we need hope, is that some fraction of those should be alive. Someone should be home. But the more we learn about what it actually takes to keep a world habitable, the more it starts to look like the real story isn't about life starting at all. It's about life lasting, and lasting is a much harder trick to pull off. Let's start with the world we can see best, the one right next door. There is a rock sitting on Mars right now. It's inside a sealed metal tube about the size of a piece of chalk. It was drilled out of a stone in the summer of 2024. The rock has small, dark markings in it. The people who found them call them poppy seeds and leopard spots. On Earth, patterns like that would be a textbook signature of microbial life. After a year of careful review, NASA's official position became that the sample contains what they call a potential biosignature. They're extremely careful with the word potential. Nobody is saying life, not yet. But the tube is still there. It's sitting on the surface of a planet that died roughly 3.5 billion years ago. And the earliest we might get it home is somewhere in the late 2030s. Think about that for a second. The most important rock sample in the history of our species is sitting on the surface of another planet in a metal canister, waiting for us to come pick it up. We can't get to it. Not for another decade at least. And in the meantime, all we have is a photograph. There's an old idea about photographs. They aren't really images of people, they're images of moments. The person you photograph will keep aging. The moment, frozen on the film, doesn't. So you end up holding in your hand a small rectangle that's a piece of time separated from the person it came from. That rock is like that. A piece of time, a piece of Martian time, maybe a piece of time when something was alive, or maybe a piece of time when no life was ever present, and the rocks just happened to assemble themselves into patterns that look like life would have made them. We don't know. The image is real. What it shows is still being worked out. If you've ever moved into a house that someone else used to live in, and you've gone up into the attic, you know the feeling. There's a box up there. The box has photos in it. Real photos, real people, real faces in clothes you don't recognize, in rooms you don't recognize, in places you've never been. You're holding pictures of people who walked through your hallway and ate in your kitchen generations before you bought the property. They're not your family, they're just people. The fact that they were there, doing ordinary things in the same physical space you now live in, is hard to absorb the first time you really notice it. Mars is like that attic. You climb up there expecting dust, expecting nothing, and instead, you find a photo album. The pictures are real. They are of someone you've never met. And the camera that took them stopped working a very long time ago. That's the situation we're in with Mars. The rock in the tube is the latest photograph from the attic. There may be others. There almost certainly are. We've been knocking on Mars's door for 60 years. Sometimes the door rattles. Sometimes a window opens. Mostly, the house is quiet. The wind blows red dust against the porch. The porch light is still on. The house is empty. But Mars isn't the only dead world. It may not even be the most important one. The one that's harder to think about, because it's our actual twin, the one we usually skip past in school, the one we file under hot rock and stop thinking about, is Venus. We don't think about Venus the way we think about Mars. Mars gets all the cultural attention. Mars is the rover planet, the future colony planet, the one people put on the cover of magazines next to a square-jawed person in a spacesuit. Venus is the one we mostly skip. You learn about Venus in school for about a week. It's the one with the runaway greenhouse, the greenhouse gone wrong example, the lesson where the teacher tells you that's what happens if a planet gets too much carbon dioxide and then you move on. That telling is wrong, or at least, it's missing the important part. Venus, on paper, is Earth, almost exactly Earth. It has roughly the same diameter as our planet, the same mass, the same density. It formed at roughly the same time out of the same protoplanetary disk from the same general mix of materials. It sits inside the inner solar system. It's our sister world, by every standard astronomers use to mean the term sister world. If you grabbed a stranger and showed them the basic specifications of two planets, one labeled Earth and one labeled Venus, and asked them which one supports life, they'd have no way to tell. And here's the part that I genuinely think people should sit with for a minute. Venus may have been habitable, with liquid water oceans on the surface, for as long as 2 to 3 billion years. That's not a wild speculation. That's the conclusion of climate models run by NASA's Goddard Institute for Space Studies. The simulations take what we know about Venus's likely early conditions, run a three-dimensional climate model forward in time, and find that under reasonable assumptions about cloud cover and rotation, Venus could have had a stable, temperate climate with surface oceans for somewhere between 2 and 3 billion years before it tipped into the state it's in now, 2 to 3 billion years. To put that in scale, complex multicellular life on Earth has been around for about 600 million years. Venus, on this timeline, had liquid surface oceans for longer than complex life has existed on Earth. 5 times as long, give or take. There was on the surface of that planet an environment that, under any reasonable definition, would have been habitable for an amount of time that dwarfs the existence of any animal anyone has ever named. Whether anything used that habitat is another question entirely. We have no fossils from Venus. We have, at this point, no surface samples from Venus. The few Soviet landers that touched down on the Venusian surface in the 1970s and early 1980s lasted, on average, less than 2 hours before the heat and pressure killed them. The longest survivor lasted just over 2 hours. The pictures it sent back show a flat, tan landscape of broken rock. The sky overhead, a heavy, sulfurous yellow. No animals, no plants. Definitely no civilizations. But the question isn't whether anything is there now. The question is whether anything was there 2 billion years ago, when the planet might have looked completely different. Then, somewhere around 700 million years ago, the conditions on Venus changed. The triggering event is debated. The leading candidates include a massive global resurfacing event where the entire surface of Venus was repaved by volcanic activity in a relatively short geological window. There's also the steady brightening of the sun, which has been increasing in luminosity. There's the possibility of a runaway volcanic outgassing episode that pumped enormous amounts of carbon dioxide into the atmosphere over a relatively short time. There's a possibility that more than one of these things happened together and crossed the threshold the climate system could no longer balance. Whatever the trigger was, the climate flipped. Water vapor, which is itself a powerful greenhouse gas, trapped more heat in the atmosphere. The hotter atmosphere held more water vapor, which trapped more heat. The oceans began to evaporate. The hotter the atmosphere got, the more the oceans evaporated. The more water vapor entered the atmosphere, the hotter the atmosphere got. That feedback loop is what scientists mean by a runaway greenhouse. By the time the runaway finished, Venus's oceans were entirely gone. The water vapor in the upper atmosphere got broken apart by solar ultraviolet radiation. The hydrogen, being light, drifted off into space. The oxygen, being heavier, mostly bonded with surface materials and got locked into rocks. The carbon dioxide, which had been dissolved in the oceans and locked up in rocks, was now free in the atmosphere, and the atmosphere just kept thickening. Today, the surface temperature on Venus averages about 462 degrees Celsius, hot enough to melt lead, hot enough that you don't need to imagine standing on it. You don't get to stand on it. You'd be dead in less than a second. The surface pressure on Venus is about 92 times Earth's atmospheric pressure. That's the pressure you'd feel at the bottom of about 900 meters of ocean. The Soviet landers that survived for those few hours did so because they were essentially deep-sea pressure vessels, built with hulls thick enough to handle the weight of an ocean's worth of atmosphere. The sky overhead, if you could somehow see it, is a thick yellow gloom full of clouds made of sulfuric acid. The clouds rain, but the rain never reaches the surface. It evaporates back into the atmosphere on the way down, because the lower atmosphere is so hot that liquid sulfuric acid can't stay liquid in it. So the sky has weather, and the weather has acid, and the acid never lands. This is what Venus is now, a place where lead would puddle on the ground, a place where the air weighs 92 times what our air weighs, and that air is poisonous and corrosive and full of acid rain that never reaches the surface. A place that is, by any reasonable definition, hell. Here's the part that makes Venus the harder world to think about than Mars. The oceans don't completely vanish. They leave a trace. If you look at the chemical composition of Venus's atmosphere with a sensitive enough instrument, and you measure the ratio of two kinds of hydrogen in the upper atmosphere, you find something that doesn't make sense unless Venus used to have a lot more water than it does now. There's regular hydrogen, the kind with one proton in the nucleus, and there's deuterium, the heavier kind with a proton and a neutron. Deuterium is rare on Earth. It makes up about 1 part in 6,400 of the hydrogen in our oceans. On Venus, the ratio of deuterium to regular hydrogen is roughly 150 times what it is on Earth. That's not a small number. That's the kind of number that has only one good explanation. Light hydrogen escapes into space more easily than heavy hydrogen, because light things move faster at any given temperature. So if you start with a planet that has both kinds of hydrogen mixed in its oceans, and you boil those oceans into the upper atmosphere, and you let solar radiation work on that water vapor for a few billion years, the regular hydrogen gets stripped away faster, and the deuterium hangs around. Over time, the ratio of heavy to light hydrogen in the remaining atmosphere goes up. So when you measure Venus's atmosphere today, and you find 150 times Earth's deuterium ratio, what you're measuring is the chemical fingerprint of an ocean's worth of water that boiled into space billions of years ago. The water is gone. The trace of the water is not gone. We don't usually think of planets as having ghosts, but Venus has one. It's chemical. It's measurable. It's there. The ocean that used to be on Venus is, in a real sense, still hanging in the air, just as a ratio of isotopes, just as a number on a spectrometer, the shape of an absence. So now we have two dead worlds in our own neighborhood. Mars, killed by a cooling core and a vanished magnetic field. Venus, killed by a runaway greenhouse and an ocean boiled into space. Different deaths, same result. Two planets, the same age, the same materials, the same construction, the same starting conditions. One in the dust, one in the fire, Earth in between. Which raises a question that ought to make anyone uncomfortable. How stable is any habitable window anywhere? If 2 of the 3 rocky planets that started inside the Sun's habitable zone have already lost their habitability by completely different mechanisms, what does that tell us about the 3rd one? This is where we have to look deeper, because as it turns out, the habitable zone itself is not a place you can plant a flag in and stay forever. It moves. When people first hear about the habitable zone, the image that gets planted in their head is a kind of permanent neighborhood. You imagine a ring around a star, and inside that ring it's just right. The planets inside the ring are the good ones. Earth is inside the ring, and that's why we get to exist. Almost none of that is right. The habitable zone is real. The math behind it is real. But the habitable zone moves. It moves because stars change. Stars are not steady. They look steady to us because human lifespans are short and stars change slowly. But over billions of years, every star brightens, cools, expands, and eventually dies. A main sequence star, the kind our Sun is, gets gradually brighter as it ages. Hydrogen in its core fuses into helium. The core becomes slightly denser. The pressure goes up. The temperature goes up. The fusion rate goes up. The star puts out more energy. Year by year, the increase is invisible. Over billions of years, it adds up. The Sun has brightened by roughly 30% since the Earth formed. That's not a minor adjustment. That's the difference between a comfortable indoor temperature and a fever. If the Sun today were as faint as it was when Earth was new, the planet would be a frozen ball. As the Sun gets brighter, the habitable zone moves outward. The orbital distance at which water can exist as a liquid pushes further from the star. The inner edge of the habitable zone, the line beyond which water would boil away under any reasonable atmospheric conditions, creeps outward year by year. Today, Earth sits comfortably inside the habitable zone. In about 1 billion years, give or take a few hundred million, the inner edge will reach Earth's orbit. That's not the immediate end of life on Earth. The mechanics are more complicated than that. As the Sun brightens, the Earth's surface warms. The warmer surface causes more water to evaporate into the upper atmosphere. The water vapor in the upper atmosphere gets broken apart by ultraviolet light. The hydrogen escapes into space, the same kind of process that played out on Venus. The oceans start to lose water. The chemistry of the surface starts to change. The kind of life that requires complex multicellular bodies and stable temperatures and oxygen and liquid water all together starts to run out of places to live. Most credible models converge on a window of somewhere between 1 and 1.5 billion years from now before complex life on Earth becomes untenable. Microbes might hang on longer. Microbes can do a lot. But the planet with forests and oceans and animals and rain and snow and seasons, that planet has roughly 1 billion good years left. If you push the timeline further, the situation gets worse. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its red giant phase. The outer layers will swell outward. The total energy output will go up by a factor of about 1,000. The orbits of the inner planets will be inside the expanding solar atmosphere. Mercury will be inside the Sun. Venus will be inside the Sun. Earth, by the most recent modeling, will most likely also be inside the Sun somewhere around 7.5 billion years from now. So the planet itself has a kind of expiration date, and the habitability of the planet has a different, earlier expiration date. The habitable zone isn't a place, it's a moment. Think of it this way. Imagine a piano. The keys you can play with one hand are limited. You have an octave, 8 white keys, 5 black keys, all sitting within reach of your fingers when your hand is on the keyboard. If you want to play notes outside that octave, you have to move your hand. The habitable zone is the playable octave for liquid water. Within that range, you can do music. The notes work. Outside the octave, the notes are too high or too low, too hot or too cold. The music falls apart. But the piano isn't stationary. Someone is slowly pushing it across the room. The playable octave is sliding outward over time. The keys you use to be able to reach keep falling off the edge of the bench. Mars's keys fell off the bench around 3.5 billion years ago. Venus's keys fell off the bench around 700 million years ago. Earth's keys are sitting roughly in the middle of the playable octave right now. The piano keeps moving. The keys keep sliding. There are other planets, ones we have found in other systems, that may already be past their playable octave. There are planets sitting in what we currently classify as the habitable zone of stars that have been around for many billions of years and have done their share of brightening and may have already shoved their habitable zone past those planets. We see them and we mark them down in the catalog, and we say liquid water could exist there. The truth is more complicated. Liquid water could exist there if the conditions are exactly right at the moment we're looking. The conditions a billion years ago might have been very different. The conditions a billion years from now will definitely be different. We're seeing a snapshot. The snapshot doesn't tell us how long the conditions have been that way or how long they'll continue. The phrase habitable zone carries a sense of permanence that the physics doesn't actually justify. Now, take that moving target and apply it to the most common kind of real estate in the galaxy. Most of the stars in the galaxy are not like the Sun. Most of the stars in the galaxy are smaller, redder, and significantly less patient with their planets. Roughly 3 out of every 4 stars in the Milky Way are something called an M-dwarf, also called a red dwarf. These are small stars, much smaller than the Sun. They're cooler than the Sun. They're dim. They are also, by a large margin, the most common kind of star in the universe. 3 out of every 4 stars you could ever visit in this galaxy are red dwarfs. 3 out of every 4 habitable zones being studied right now are around red dwarfs. 3 out of every 4 exoplanet announcements that include the phrase Earth-sized planet in the habitable zone are referring to planets that orbit red dwarfs. So when we talk about how many habitable worlds might be out there, we're mostly talking about red dwarfs by default. The math just works out that way. And that matters because red dwarfs are not gentle. They are magnetically furious. They produce more flares. Red dwarfs have flares that can be, in some cases, 10,000 times more powerful than the most powerful solar flare our Sun has ever been recorded to produce. A flare that on the Sun would briefly knock out radio communications across half the Earth would, on a red dwarf, deliver radiation across the entire inner star system in concentrations that no biology we know would survive without serious shielding. And these flares aren't rare events on red dwarfs. They are routine. The TRAPPIST-1 system, which is 40 light-years away, contains 7 Earth-sized planets, several of which sit in the conventional habitable zone of their host star. It looks, on paper, like exactly the kind of place we'd want to look for life. In 2025, JWST observations of TRAPPIST-1 measured its flare activity over a sustained period and found that the star produces roughly 6 flares per day. 6 flares per day, every day, for billions of years. The planets sitting in the habitable zone of that star, which orbit closer to it than Mercury orbits the Sun, are taking those flares full in the face. They are right next to the speaker. The volume is at maximum. The volume has been at maximum since the system formed. What does that do to a planet? Laboratory studies have taken cultures of various Earth microbes, including the most radiation-tolerant ones we know about, like Deinococcus radiodurans, and exposed them to simulated red dwarf flare radiation. The general picture is that flares of this magnitude repeated at this frequency are enough to sterilize all but the hardiest microbes from any unprotected surface. Anything sitting in shallow water, in topsoil, in exposed environments gets cooked. Some life might survive deep underground, in subsurface oceans below ice. But the kinds of habitable surface conditions that complex life on Earth depends on, the open sky, the running water, the photosynthesizing plants, are very hard to maintain on a planet that's getting hit with that kind of radiation every few hours, forever. There's another problem with red dwarf habitable zones, tidal locking. Because the habitable zone around a red dwarf is so close to the star, the gravitational interactions are strong enough to lock the planet's rotation to its orbit. The same face always points at the star. The other face never sees the star. One hemisphere is in permanent day, baking under a red sun that never moves in the sky. The other hemisphere is in permanent night, cold enough that even atmospheric gases might condense and snow out on the surface. The boundary between the two, the terminator, is a narrow strip of perpetual twilight. That terminator is the only zone where the temperatures might be reasonable for surface water, a thin ring of habitability on a planet that's otherwise either too hot or too cold. There are models that suggest a thick atmosphere could redistribute heat and make more of the planet livable. There are other models that suggest the atmosphere on the day side might just slowly evaporate and migrate to the night side and freeze out, leaving you with a planet that has a frozen ocean of nitrogen and oxygen on one hemisphere and no atmosphere at all on the other. The honest answer is that tidally locked habitable zone planets might be habitable in some cases, with the right atmosphere, with the right luck. Or they might just be split planets, half ovens, half meat lockers, with a narrow band in between where nothing has the time to settle in. So when we count habitable zone planets in the catalogs, and we end up at numbers like tens of billions across the galaxy, we have to be honest about what that number means. Most of those planets orbit red dwarfs. Most of them are sitting closer to their star than Mercury is to ours. Most of them are getting hit with flares many orders of magnitude more powerful than any flare our Sun produces, several times a day, for the entire life of the star. Many of them are tidally locked. The phrase habitable zone, as applied to these worlds, is doing some heavy lifting that it doesn't really earn. 3 out of every 4 lottery tickets we have for finding life are these worlds. Most of the candidates for life that we're currently studying are sitting inside a fight that never ends. So we've talked about a lot of dead worlds. Worlds where the conditions left. Worlds where the star never let them settle. Worlds in the wrong era of their host star's life. Worlds whose habitability is on a moving target that's pushing past them. It's worth pausing here because so far we've been talking about other people's deaths, other planets, other systems, other stars. The harder question is what Earth's own history actually looks like. Because Earth, the planet that we usually treat as the steady one, the consistent one, the one that worked, has more endings in it than most people realize. The lights almost went out here repeatedly. And once, they almost went out because life itself learned to do something it had never done before. The standard story about Earth is that we got lucky. The sun is calm, the orbit is stable, the moon stabilized our axial tilt, the magnetic field holds, the atmosphere holds, the water holds, life showed up, life stuck around. That story is true in its broad outline, but it's also not the whole picture. Earth has come very close to going dark more than once. The fossil record contains evidence of 5 major mass extinctions, plus a long list of smaller ones. The Permian-Triassic extinction, 252 million years ago, is sometimes called the Great Dying. Roughly 96% of marine species died off. Roughly 70% of terrestrial vertebrate species. Insects had the only mass extinction event in their history. The fossil record on either side of that boundary looks like 2 different planets. Almost nothing made it across. It took the planet between 5 and 10 million years to fully recover ecological complexity. That's the worst one we know about in the fossil record. But it's not the worst extinction event Earth has ever been through. The worst one happened so long ago that it almost doesn't have a fossil record at all. It happened to single-celled organisms in shallow seas more than 2 billion years before any of the famous extinction events that have names you might recognize. It's called the Great Oxidation Event. And it's the strangest catastrophe in the planet's history because it wasn't caused by an asteroid or a volcano or a comet. It was caused by life itself. For about the first 2 billion years of life on Earth, the dominant organisms were anaerobic. They got their energy from chemistry that didn't involve oxygen. There wasn't any free oxygen in the atmosphere to use. The bacteria and archaea that lived on the early Earth used chemistry that we'd find profoundly strange today. They were the entire biosphere for about 2 billion years. Then a particular group of bacteria, the ancestors of what we now call cyanobacteria, evolved a new trick. They learned how to do photosynthesis, using water as the electron donor. As a byproduct of that chemistry, they released oxygen, free oxygen, pure O2 gas. It started slowly. The early oxygen-producing cyanobacteria pumped oxygen into the surrounding water, and the oxygen mostly got eaten up by chemical reactions with dissolved iron and other reduced compounds in the oceans. There was, for a long time, an oxygen sink. The free oxygen was being produced, but the oceans absorbed it almost as fast as it came out. Eventually, the sinks filled up. The dissolved iron mostly precipitated out. The oxygen had nowhere left to go but up. It started accumulating in the atmosphere. For most of the life on Earth at the time, that was a catastrophe. Oxygen, for an organism that evolved without it, is a poison. It tears apart cellular chemistry. The anaerobic microbes that had spent 2 billion years building up the entire biosphere of Earth were not equipped to handle it. The rise of atmospheric oxygen killed off something like 80 to 99% of life on Earth at the time. The first true mass extinction in the planet's history wasn't caused by a rock from space. It was caused by life learning to do something it had never done before. The first mass extinction was the air we now require to breathe. Everything you've inhaled today is part of the same atmosphere that 2.5 billion years ago was a planetary disaster. The oxygen that you need to keep your brain working is the same molecule that exterminated most of the planet's biosphere the first time it showed up at high concentrations. It was a poison in its day. It became a fuel later after enough organisms evolved to handle it. The recovery from that event took a very long time. Between the Great Oxidation Event and the appearance of the first complex multicellular organisms in the fossil record, there's a stretch of about 1 billion years where the geological evidence is famously dull. It gets called the boring billion. Not much going on in the rocks. Microbial life is around. It's quiet. It's catching its breath. The biosphere has been knocked back so hard that it spends 1 billion years just getting reorganized. This should change how you think about life on Earth. It changes how I think about it. The picture of Earth as a stable, life-friendly planet is true, but only in the broadest sense. Yes, the planet has supported life continuously for about 4 billion years, but within that broad continuity, there have been at least 5 major resets, plus the largest reset of all, the oxygen catastrophe. Almost everything alive has died multiple times in different ways for different reasons. The thread of life on Earth is not a thick rope. It's a series of thin filaments, some of which broke, some of which survived, with the surviving filaments carrying everything forward each time. The relevance of all this to the question of life on other planets is straightforward, but unsettling. If life on Earth, on the planet we're currently calling the success story, has almost been wiped out multiple times, and once was nearly wiped out by its own metabolic byproducts, what are the odds that life elsewhere has navigated its similar transitions successfully? What are the odds that a young planet somewhere out there evolved photosynthesis in some form and then choked on its own oxygen and never recovered? We have one example of life that survived its own evolution. The fact that we exist means it can happen. The fact that it almost didn't, on the only example we have, means it might fail more often than it succeeds. All of which raises a different question. We've been talking about what happens to life once it gets going. We haven't talked yet about how often life actually gets going in the first place. And it turns out that's a question we don't have a good answer for either. We have exactly one example. And one example doesn't tell you much about how common the thing actually is. There's a tendency, when we talk about habitable planets, to assume that habitability and inhabitation are the same word. They are not. They are not even close. Habitability is a description of conditions. Inhabitation is a description of what's actually living there. The first is a kind of resume. The second is whether anybody ever showed up to do the job. Here's what we actually know about life starting on a planet. We know it can happen. We know it because we are on a planet where it's happened. That's one data point. That's the entire data set. We do not know how often it happens on a planet where the conditions allow it. We don't know if it always happens, given enough time. We don't know if it usually fails. Earth had liquid surface water for somewhere between 100 million and 700 million years before there is any clear evidence of life. That's the gap between the planet being habitable and the planet being inhabited on the only world we know that is both. That gap matters. It matters because we don't know what happened during it. Was life almost instantaneous as soon as the conditions were right, with the apparent gap just being an artifact of an incomplete rock record? Or did it take 500 million years of chemistry running and rerunning before the first self-sustaining biological system finally took hold? The answer to that question would tell us more than almost anything else, whether life is common in the universe or vanishingly rare. The trouble is, we don't know. The earliest fossils on Earth are debated. The earliest biosignatures are debated. The honest answer is that life on Earth got started somewhere between very quickly and very slowly, and we can't tell which. The transition from non-living chemistry to a self-sustaining, self-replicating, evolving cell is a hard problem. It requires information storage like DNA or RNA or something equivalent. It requires a way to translate that information into action, like proteins or their equivalents. It requires a way to enclose the system, like a cell membrane. It requires an energy source. It requires a way to make copies that are imperfect enough that variation can accumulate, but accurate enough that the system doesn't fall apart. You need all of those things in some form working together on a planet where they have time to assemble. None of that is trivial. There are biochemists who think the assembly of the first cell from prebiotic chemistry is a problem so hard that it might happen only once in the lifetime of an entire galaxy, by sheer statistical chance. There are biochemists who think it's so favorable that it should happen on any planet with the right chemistry within a few million years. Both groups are smart. Both groups are working on the same evidence. They disagree because the problem is genuinely hard, and the available evidence is